Similarly, acceleration is rate of change of velocity or velocity by time. So it becomes L power minus 1 and time power minus 2. In a correct equation which is representing relation between any physical quantity, all the terms on both sides of the equation must have the same dimension. We already know that C is half. So for the equation to be 0, A will be minus half. Hello students, welcome to this third session on units and measurements from your first PUC Physics. I am Madhu R from the Department of Physics at Vidhyaashram PU College, Mysuru, your Temple of Excellence. Let us have a quick recap of what we covered in the previous session. We covered topics like accuracy, precision, errors in measurement, least count, significant figures, what are the rules applicable for identifying the number of significant figures, how do you do arithmetic operations when there are significant figures, and what are the rules for rounding off the significant figures. These were a few of the topics that we covered in the previous session. Moving on, let us today study about dimensions, one of the very foundation topics in physics. Now, what are dimensions? Let us have a first look at dimensions. Dimensions of any physical quantity are the power to which the base quantities are raised. Sir, what do you mean by that? Let me say, if the length of a table is represented by meter, the dimension of that is said to be L within square brackets. Dimensions of all physical quantities are denoted with square brackets. Now I said that dimensions of any physical quantity are the power to which the base quantities are raised to represent that physical quantity. Meaning, suppose I have to represent the dimension of area. The unit is meter square. I am raising the base quantity to the power 2 so that I can represent area. Okay, this is what we said here. The dimensions of a physical quantity are the power to which the base quantities are raised. Similarly, for volume, the unit is meter cube. I can represent the dimension by raising the power of L to 3. This is one basic way of understanding what dimensions are in measurements. Dimension of a physical quantity will explain its relationship with the fundamental quantity. For example, if I take area, I understand that there are 2 dimensions of length. In volume, there are 3 dimensions of length. This is what we mean here, saying that it explains its relationship with the basic or fundamental quantity. All the derived fundamental quantities can be expressed in terms of some or the other combination of the 7 fundamental quantities. If you can go back to my first session, we had explained what are the 7 fundamental quantities under SI system. Okay, let us have a look at how those 7 fundamental quantities are expressed in terms of dimensions. Symbols for dimensions of fundamental quantity. Length is expressed as L within capital brackets. Similarly, mass is expressed as M. Time is expressed as capital T. Current is expressed as capital A. Thermodynamic temperature as capital K. If you remember, Kelvin is the unit. Luminous intensity is expressed as CD, candela. Amount of substance is expressed as MOL within square bracket. The unit was mole. Okay. So with the help of these fundamental quantities, I will be in a position to express any of the derived quantities. I have already explained what is area. I have already explained what is volume. Let us now have a look at few of the other derived quantities. Length is expressed as L, or conventionally I can express it as 0 dimensions of mass, 1 dimension of L, and 0 dimensions of time. So this is how we generally express any quantity. Okay, I will try to express it in terms of mass, length, and time. If there is no dimension of any one of these quantities, I will raise it to the power 0. Okay. Now let us have a look at density. For density, the unit is kg per meter cube or mass by volume. So I can express this as 1 unit of mass and then 3 units of length in the negative direction, and there is no dimension of time, 0 dimension of time. Okay. Similarly, I can express it for any other quantities that you know or any other derived quantities that you know. Velocity is distance by time, or rather displacement by time. 1 unit of length and minus 1 dimension in time. Similarly, acceleration is rate of change of velocity or velocity by time. So it becomes L power minus 1 and time power minus 2. You can also express force, you can express energy, you can express heat, you can express power. Any of the derived quantities can be expressed in terms of mass, length and time. This is what is the essence of dimensions. Okay. Let us go on and understand further what dimensionless quantities mean. I told you what dimensions mean. There are certain quantities which don't have dimensions. Two types in that. One is a variable, the other is a constant. Variable obviously has changes in its value. What are examples? Angle, specific gravity, strain, etc. are variables which do not have any dimensions. That is why they are called as dimensionless variables. Similarly, all numbers, all pure numbers, along with numbers like pi, e, Euler's constant, etc., they are dimensionless constants because their value do not change. So it is not that all quantities have dimension. There are certain quantities which do not have dimensions and they are called as dimensionless quantities. Okay. One is the variable like angle, strain, etc. The other one is a constant like all the numbers pi, e, etc. Okay. Moving on, let us try to understand what is principle of homogeneity. Principle of homogeneity is required in an application of dimensional analysis where we equate the LHS of an equation to the RHS of an equation and try to find out the dimensions of all the terminologies in both the sides of the equation. Okay. In any correct equation representing the relation between physical quantities, it may be any equation. If it is representing the relation between physical quantities, dimensions of all the terms must be same on both the sides. Say for example, okay, energy or kinetic energy is given by the equation half mv squared. Okay, it is given by the equation half mv squared. Kinetic energy is given by the equation kg meter square per second square. So the dimensional equation becomes for kg mass there is 1, for length there is 2 and for time there is minus 2. This is LHS. Now coming to the RHS. mv square, I am considering only mv square because half is a dimensionless constant, so it does not have any dimensions. Now what do I check? Mass, okay, 1 dimension. Then v square, the unit for velocity is meter per second. For meter there is 1 dimension of length, for per second there is minus 1 dimension of time. So this is L t to the power minus 1 whole square. So this becomes m L square t to the power minus 2. Okay. So now you can understand that in that equation for kinetic energy, okay, the dimensions of all the terms on both the sides of the equation are the same. It is ml square minus 2, ml square minus 2. If there are multiple terms also, all the terms must be having the same dimensions. We'll have a look at few examples later, but for now let us try to understand the principle of homogeneity. Quantities having the same dimensions can only be added, subtracted or equated. If the dimensions of terminologies are different, then you cannot do these arithmetic operations. All the terms on both sides of the physical equation must have the same dimensions. Otherwise, we say that the equation is not correct. If an equation is dimensionally correct, the dimensions of quantities on the left-hand side must be equal to the dimension of the quantities on the right-hand side. So, principle of homogeneity lets us know that in a correct equation, which is representing a relation between any physical quantity, all the terms on both sides of the equation must have the same dimension. Okay? So, using this principle of homogeneity, let us now try to check the correctness of a few equations. Okay? I have now taken the examples of equations of motion. Okay, let us check them one by one. What are those? The first equation says V is equal to V naught plus AT. As we all know, V is the final velocity. V naught is the initial velocity. A is the acceleration. And T is the time taken. Now, from the principle of homogeneity, we have understood that all the terminologies in this equation on both the sides must have the same dimension. So, let us check all the terms one by one. First one is the velocity. Then we have the initial velocity. Then we have the terminology of A and T. What is velocity? Velocity is displacement by time. The unit is meter per second. For meter, you have got one dimension of length, and for second, you have got one dimension of time in the negative. So, the dimension of the LHS terminology is L into T to the power minus 1. Similarly, V naught is also velocity. It is the initial velocity with the same unit of meter per second. So, the dimension does not change. It is L T to the power minus 1. Now, moving on to the third terminology, which is a product of acceleration and time. What is the unit for acceleration? The unit for acceleration is meter per second square. Meter per second square multiplied by time, whose unit is in seconds. Now, if I solve this, this will once again be meter per second. For meter, you have L to the power 1, and for per second, you have time T to the power minus 1. With this, I can understand that the terms on both sides of the equation have the same dimension. In the LHS as well as the RHS, all the three terms has the same dimension. Hence, I can conclude that this equation is dimensionally correct. This is what we have started. Check the correctness of a physical equation using dimensional analysis. The procedure adopted here for checking the correctness of the equation is called as dimensional analysis. Let us take a few more examples to understand this concept. The second law of motion, which says that x is equal to v naught t plus half at square, where x is displacement, v naught is initial velocity, a is acceleration, and t is time taken. With the usual notations, let us try and check if this physical equation has the same dimensions for all the terms on both the sides of the equation. On the left hand side, I have got displacement. On the right hand side, I have got two terminologies, V naught T and half AT square. Let us first check for LHS. X is nothing but displacement. The unit for displacement in SI units is meter. So the dimension for this terminology will be L, the length. Let us move on to the next terminology, which is V naught T. V naught is the initial velocity and T is the time taken. For velocity, the unit is meter per second into time, the unit is second. So the second and second get cancelled off, you are left with meter. The dimension for meter is L. The dimension for meter is L. Let us move on to the last term, which is half AT square. We know that the number half is a dimensionless constant. There is no dimension to this term half. So let us concentrate on A and T square. A is acceleration, whose unit is meter per second square, and then there is a time square. So this is second square. The second square gets cancelled. Okay, you are left with the unit meter, whose dimension is L. You can observe that all the three terms on both the sides of the equation has the same dimension, one dimension in length. Hence, I can conclude that this equation is dimensionally correct. Once we have proved two equations of motion, let us also try the third equation of motion and check if it is dimensionally correct. The third equation of motion says that V square is equal to V naught square plus 2AX, where V is the final velocity, V naught is the initial velocity, A is the acceleration, and T was the time taken. Here X is the displacement. Let us check all the three terms on both the sides of the equation. We have got V square, we have got V naught square, and we have got 2AX. Let us check the dimension of all these three terminologies. V is the velocity. Velocity is given by meter per second. Here there is a square, so meter per second whole square, where you have got two dimensions of meter. So this is meter square per second square. If I write the dimensions of this, 2 dimensions of length and minus 2 dimensions of t. So the LHS has a dimension of 2 in length and minus 2 in time. Let us now check the other terminologies. V naught square is nothing but the initial velocity. So even for initial velocity, you have meter per second as the unit, whole square. Same process follows. The dimension is L square t to the power minus 2. Now moving on to the third terminology in the equation, which is 2AX. We already know that 2 is a dimensionless number. It does not have any dimensions, also called as a dimensionless constant. So let us concentrate on AX. A is the acceleration. So the unit for that is meter per second square into displacement. Displacement is meter. The unit for displacement is meter in SI system. So combining, we get meter square per second square. Now if I write the dimension of this, it has got 2 dimensions in length and minus 2 dimensions in t. You can clearly observe that all the three terminologies on both the sides of the equation has the same dimension of L to the power 2 and t to the power minus 2. Hence, we can conclude that this equation of motion is dimensionally correct. Now, is this the only application of dimensions, checking the correctness? No, you can also derive certain relations. Let us now try to derive the relation between some physical quantities. Let us take the example of the period of oscillation of a simple pendulum. The period of oscillation T depends upon the length, the mass of the bob, and the acceleration due to gravity. Let us take the mathematical equation. T, the time period, is proportional to the length, the mass of the bob, and the acceleration due to gravity. I don't know what is in the powers, so let me imagine it as L to the power A, M to the power B, and G to the power C. How to mathematically resolve this? Let T be equal to, let K be some constant, L to the power A, M to the power B, and G to the power C. Let me try and define the definitions for all these things. What is time? I can represent time by M0, L0, and T to the power 1. This will be equal to K into L is length, so this is L to the power A. M, as you can see here, is the mass of the bob, so this is M to the power B. What is gravity? Acceleration due to gravity is represented by the unit meter per second square. So this is length and time to the power minus 2. So this is length time to the power minus 2 whole to the power C. Okay. So length to the power A, mass to the power B, and gravity to the power C. So this will be equal to K into L to the power A, M to the power B, again L to the power C, and T to the power minus 2C. Please observe here, I have two dimensions of length. So let me add the powers. Okay. Theory of indices, A to the power M into A to the power N. A to the power M into A to the power N is equal to A to the power M plus N. That is what I am employing here. So this is equal to K into L to the power A plus C, M to the power B, and T to the power minus 2C. On the left hand side, I have M to the power 0, L to the power 0, T to the power 1. Okay. By the principle of homogeneity, I understand that whatever is in the power of M, L, and T can be equated to the LHS and the RHS. So let me consider M to the power 0 to M to the power B. So what do I have? I have B is equal to 0. Next, let me take into account T to the power. I have T to the power 1 and I have T to the power minus 2C. So this is minus 2C equals 1, or C is equal to minus half. Please remember, B equals 0, C equals minus half. Let me check the third part, which is regarding the length. Length to the power A plus C, here you have length to the power 0, or the dimensions of length. So A plus C equals 0, or A equals minus C. This is minus of minus half. So A will be plus half. So with the help of dimensional analysis, I have found out the powers. B is 0, C is minus half, A is half. Let me substitute it back in the original equation. So it comes to T equals K into L to the power A. So L to the power half. M to the power B. B is 0. And then G to the power C. C is minus half. So you are left with K into L to the power half, G to the power minus half. What is to the power half? Power half is nothing but square root. So this is square root L into 1 by square root G. So I am left with T is equal to K into square root of L by G. Okay, I am left with the equation T is equal to K into square root of L by G, where K is proportionality constant. Please remember, with the help of dimensional analysis, I will not be able to find out what is the exact value of K. I can only say that it is somewhat related between what? The period of oscillation T, the length, and the gravitational force. Okay. So this is how you can derive relations between physical quantities. What are the limitations of dimensional analysis? One by one. The first and the foremost thing is dimensionally correct equations need not be actually correct. What do you mean by that? We had the equation x is equal to v naught t plus half at square. In this equation, we know that this number half is a dimensionless constant. If I replace that by 2 also, dimensionally the equation will remain correct. If I replace that half with any other number, the equation remains to be dimensionally correct, but actually it will not be correct. So please understand that this is the limitation. Correctness of constants appearing in an equation cannot be verified. So whatever I told you in the first sentence, that itself holds good here. I don't know if this constant is exact value or not. I don't know if half is the proper value or 2 or some other number. That is one more limitation. Then we have equations involving trigonometric and exponential functions. Wherever there are exponential functions to the power of or some trigonometric functions, it cannot be verified. An equation can be derived. The derivation of equation, not checking the correctness. The derivation of equations is possible only for product type. If there are operations like plus or minus, then you cannot derive that equation. It is not possible with dimensional analysis. While deriving an equation, value of the constant of proportionality cannot be obtained. In the previous equation, we had imagined that to be K. I don't know what its exact value is. Of course, when you study physics, you will understand that it is 2 pi. Okay? Then, this method works only if there are as many equations as the number of unknowns. If you have 3 unknowns, then there must be 3 equations. If there are 5 unknowns, there must be 5 equations. So with the number of unknowns increasing, the number of equations will also increase, and thereby the complexity will also increase. So these are some of the limitations of this dimensional analysis. So today, let us have a quick recap. Today we have studied about the dimensions. What are the dimensions for the fundamental units? How they can be correlated with the derived units by rising to its power. What is dimensional analysis? How to check the correctness of the equation, and how to derive at physical equations. We have also had a look at the limitations of dimensional analysis. Have a wonderful learning experience. Thank you.